Yeah, okay, so the limit is the difference is where, oh, okay, it's just the same, it's a similar
almost the
function.
same, right? Almost the same. And we can still use it, same method, very similar method. So just 6 minus 4 then, right? Yes, very nice.
Yeah, this is pretty simple, all things considered.
Yeah, they started with this and they want to accumulate more complicated stuff. So eventually this is 2. How about product?
Oh, okay, well, it's pretty similar. It's just basically like a function.
Yeah. So let's use this product.
So it's like,
What, -4 can be 1, right? Yes, very nice. I'm gonna introduce you to the complicated calculation.
yeah.
So just basically -4 times -5, which is 20. Yeah, they combined, the sum, the product,
Okay,
and the
so
difference.
do we graph it from here? How do we find the limit?
Well, basically, which is substitute, right? Because everything basically substitution, all this theorem that we learned in the previous 2 minutes, it's all just substitution, right? 3,
Yeah.
eliminate 3, so 3 times a -2 and plus minus a 5. Just -11, right?
Yeah, okay.
And then b is also 5x squared, also just 5 times 2 squared, which is 20. Does it make sense? This
Okay,
example
so
5?
3 times, no, wait, no, can you give
Oh,
me a second?
sure.
Okay, so 5 minus 5 times 2 to the power of 2 equals 20. Okay, oh, wait, are you referring to the second one? Huh?
Oh, yeah, this is the second one, and this is the first one.
Oh, okay, yeah. Okay, so that's the first one. So 3 times, oh. Okay, yeah, I get it. -6 minus 5. So the limit is -11.
Yeah.
And this one, the limit is 20. Okay,
Yeah.
got it.
Mm.
That makes sense.
And then we go on with, oh, he just said because of this, maybe we can introduce this then. So 5 is a, and x is x, and n is 2, or 2 is n. And he's also using substitution. All this is done by substitution. In the old time, I just remember the substitution. The substitution, right? Just substitute c equals to x, right? X equals to c. So the limit is ac to n's power. Does it make sense?
Yeah, okay.
That's making sense a little, right?
Yeah.
That's making sense. Then I don't have to prove it. So, oh, this is the proving. So I don't really need the proving if you think it's making sense. Let's do example 6 then.
Okay. Oh, okay. I think I'm getting the hang of it now. The limit is -32.
Yeah, it's basically by substitution. All this, basically all this kind of form saying substitution is working. That's how I remember it. And now we introduce, we have ax to the nth power. Now we have polynomial function. Which can also be done by substitute, basically. Still substitution is working.
Oh, okay. Okay, so if it's a polynomial, then we just substitute it in, and then
Yeah.
that equals. Doesn't that work for non-polynomials too?
Not exactly. We have to prove it later. Not all of them. And also, polynomial function is all this kind of graphing. It must be working, right? See, getting closer from the graph, we can also see that. So basically substitution, right?
So,
Does that make sense?
so does it work for the monomial too or not?
No. Only like a polynomial so far.
Why not? Why can't you just substitute Cn?
You mean for the non-polynomial?
Yeah, why can't you just substitute like Cn most of the
Well,
time?
not
I
all
thought
the
that was
time. It's like we kind of prove it every time. See, even here I prove it. We use the theorem as the foundation. Each limit is timing it, so that's why you can find all this by substitution. I substitute basically when you can actually
Aren't
prove
you
it.
still substituting though? You substitute when what?
Yeah, so this is working, right? And for polynomial, I can also prove it, so that's why I can accept it as a theorem. But for the non-polynomial, well, not so much. We don't have that.
Oh, okay. So it just doesn't apply sometimes for monomials.
Yeah. Some of them is, so we're gonna keep finding whatever that we can. You can take a look at this proving process. You see, each part is basically what we have the theorem before, right? Because it's x and power thing, right? This is all proved. This can be done by substitution, right?
Yeah, okay.
So that's why each term can be using substitution to find the limit. So the entire thing can be can be used.
Okay, so let me read that. So so the polynomial, you can prove that because and then you put that in there. Oh. Okay, I kind of get it.
Which means just each term, we basically separate the polynomial in each kind of term, right? All this kind of term. But each one does, well, basically each one satisfies this then, right? So which is working. The limit substitution, find the limit is working. So it's still using substitution. And so that one, okay, then we can do this with substitution, right? Basically substitute, right? We want to find the limit.
Okay, yeah, so first I factor it. Oh wait, we can just
substitute. Sure.
Yeah, we can just do it. So 5.
Yeah.
Oh, it's 50.
Yeah. So still can summarize all this by, well, as long as all in the proof theorem, I can say substitution is working. but not all the time. So let's see what else is in this range. And now,
Yeah.
if they say fx have a limit around when x approximates c, I mean, if the limit does exist, and we make it into 2, and it's an integer. So, and this is working then, which is still kind of like substitution, a little bit.
Okay, and then there's okay, so then n, why does it have to be greater? Oh, right, yeah, because of that. Okay, so they both have to be defined.
Yeah. So power is working,
Okay.
and integer power is working, positive integer power is working, and well, and then square root, no, nth root also working. So they have to narrow it into n equals to positive integer higher than 2 equals to 1 doesn't really count. Okay? Is this making sense? Is this true? We can take a look at the example. This is the example by all this. This is this, right?
Yeah, sorry, this is kind of harder. It's like newer, I guess. It's like I don't know. We just didn't. I've never learned. Okay,
Yeah. We can just do it. Let's just do the example
okay,
and think about whether it's
equals.
working or not.
How can I prove this work? I guess I can substitute in there. Okay, so
Well, if you
then
want to prove, you can graph it and prove it. Negative 3 to the fourth power.
minus 2, 4 equals 16.
Yeah. Does A feels okay?
Yeah, I think so. And for like 3 from the original one, if we substitute in 1, then that's just that's about this. And
Yeah.
then that's okay.
Yeah.
I think I know. Okay. Is this just defined?
Probably is because you have fourth power. You make it positive again anyway. You make a fourth power and then like 1/3 power. Right? So this is a B, right?
Yeah, B. Is that about right?
Yeah. So B is basically using this one, right? Using the second one. And root of fx. And then C.
Okay, number C, lim 5. Okay, I can barely see it. Okay.
Mm.
Mine.
-1. Okay.
I wrote this on a calculator. Oh, it's just -1.
Yeah. Wait, it's +1, right? Because when you
I
do
put it on the
negative,
calculator, -1 to the power of 4/3. Okay.
-1 to 4th power, and then 1/3 power. So this one is already making 1/3 power, and this 1, right?
Oh,
That's
okay.
1.
Yeah.
Mhm.
Sorry, I guess the calculator, I just didn't put it in the calculator right.
Probably bracket thing.
Yeah, probably.
Hmm.
I did put it in brackets though, so I don't really get it.
Okay. 4/3. Okay. If this is working, and then how about two functions divided by each other? I can find
Okay.
the numerator function limit and denominator limit and divide.
Okay, we have to find this one now.
So we can
So
use
that
this.
equals limit. Give me a second. Also, wait, for monomials, what do you do when you can't substitute in the limit?
We normally graph it to see,
Oh, yeah,
if
okay.
it's really getting close to that point or not. That's more vivid, right?
Yeah, this is polynomial. I can just use. Okay. Okay, it's like 6/7.
Yeah, good. And also getting the graph, you can also see it's really that. So it's kind of prove it. The graphing can save us in here, making a little sense. How about 10?
Okay, so minus. Okay, so that way, 3 -9, yeah.
Yeah.
It's kind of just undefined, I guess.
Oh.
Is it minus or plus? There's this little white line in. Oh, okay, it's just undefined.
Well, if you substitute that as undefined, right?
Yeah.
If your substitution is not working, sometimes the limit still exists. We learned a little bit before, right? Remember? It's remember
Yeah.
sine x over x, right? Substitution is not working. I mean, if you direct step 0 is not working, but if you substitute 0.001, there is a limit, right? So that might work for this one too, which is let's see. I can check it by the graphing later, but now I can use factorization a little bit. This is x minus 3 and x plus 2, right? Denominator. And denominator is x plus 3 and x minus 3. I can simplify this and then find x plus 2 over x plus 3. In there, I do have a limit, right?
Yeah, okay. So you just Okay, so you have to, oh, okay, so you just separate it out, but then you have a limit. Okay, that makes sense.
Mm.
Yeah, and then you substitute in 3 plus 2 over. Okay, yeah, that makes sense.
Yeah, it's so, and also the graphing tells that it does have a limit there if you throw in like decimals. And also I can prove it because I can substitute 2.99, right? Or 3.01. If I substitute, this one is not 0, so this one must be simplified with this one, right? So which is working a little.
Yeah, okay. Oh, wait, can I go to the bathroom really quick?
Sure. Cool.
I'm back.
Let's see. Oh. That division. So now we proved some, although it seems like undefined, but the limit can still exist, right?
Yeah,
Question A,
okay.
right? And then let's see question B. Actually, I have a
Okay.
hesitation about A. I mean, let me be honest. I
Oh,
have a hesitation about A. So that, well, I did the graph, as calculator the graph, some of them, it seems like really okay. So how about B?
I guess, wait, x minus sine 1 or something? I don't know. I'm trying to like factor out x, but is
Yeah.
that possible?
Oh,
Or
no,
is it
that
just,
is not
okay,
possible.
yeah,
We don't really
okay,
have
yeah.
that. But we do have
Sorry,
this.
I just wanted to check that. I was like, oh,
It's
okay,
a good
maybe I'm.
direction. Actually, we should use that direction, but not.
Okay, 0 minus sine 0 over 0 equals undefined. Okay, how do I do it in like a better direction?
How do I pretend? For example, I pretend this is also something Newton did, also not very reliable, but generally is. So, for example, if it is 0.00001, I can still simplify this to 5 minus sine x over x. Does that make sense?
Yeah, okay.
And then, well, 5, the limit is just 5, right? And this one, we already did that. This one is 1, remember? Sine x over x when x approximates 0, that's 1. The limit is for that one when x approximates 0, it's 1. Does it make sense?
Yeah, okay.
So it's basically 5 minus 1 is 4, which is the final limit. These two are both require some transformation. You change the form, and then you can do it. Otherwise, it's undefined.
Five, oh, sine x, oh, okay. 5 over x minus sine x, oh yeah, it's just 5. 5 minus sine x over x, which equals, sine x equals, over x equals 1.
Yeah.
Why?
Oh, you prove it, remember? You substitute sine 0.0001 and with
Oh, yeah.
0.0001, okay?
So that equals 1. Oh,
Yeah,
okay, yeah, that
equals to
makes sense. So minus
0.999
1
something.
equals 4. Yeah, okay, I remembered.
So, and also you can be proved by graphing it, and it's already there. Although it's not, it's a hole in there, but you can find the limit.
Yeah.
So change the form. If you can't define it, you change the form. If you change the form, you still can't find it. You probably, well, it just there, you can't find it. 11.
Okay. Wait, didn't we already do this?
Yes, this time he wanted you to. The last time you using substitution, right? Oh wait, you use factorization and then substitution.
Yeah, that's what I did.
This one he basically proved that this is really something that we can use. It's you're gonna use the same method anyway. Yeah, you're right. We did this one.
Oh. It's just undefined if I substitute. Okay. How do I do this?
Oh, factorization. Wait, you did factorization last time, which I didn't really recognize. right? This 2, one factor. There's 2, common factor x minus 2. Right? This one is becoming x squared.
Oh, okay. Sorry, I thought you were supposed to do something different besides factor it. Sorry. Yeah, sorry, I did it the last time. Sorry. I just thought we were supposed to be doing something different. So okay, yeah, I can do it though.
Mm.
6/5. That's the limit.
6/5. Okay. X. This is x cube. Let me see. I think there's x cube. There's x cube here. This one you get the common factor x cube, and you get x minus 2. So this one is x cube plus 1, right?
Yeah.
So which is 2 squared plus 2 over 2 cubed plus 1. Wait, x plus, wait, let me think. That's a 4 also. So this one is a 4. Is that?
Oh, it's +4. Okay.
Yeah.
Sorry, sorry. Sorry, that's kind of stupid. I was just missing something. So just doing it from memory.
I think you skipped
Yeah,
a
it's 4.
step. I couldn't do that directly. I have to
No,
use
it's
it.
not that I skipped a step. It's just that I was trying to factor it and then I didn't remember x power 2 plus. It's fine. Okay,
Okay.
so yeah.
Let's factor this a little.
Sorry, it's just I was trying to do it. I was like, okay, I'm just gonna do this really quickly. I'm not going.
Oh,
And then
that's
I
why.
just yeah, I just did it really
Yeah.
quickly in my head and like
Yeah, you did it right last time. So
yeah,
8
I'm sorry.
over, it's okay. 8 over 9, right? Yeah. It also can be
Yeah, sorry. I
proved.
was just trying to do it like really quickly in my head because I didn't want to redo it.
Yeah,
If that
yeah,
made
yeah,
you.
yeah. You did great last time. Let's say this is 11. Also can be proved by drawing the graph. Oh, this is also something Newton did at the time. People didn't believe him because the limit, no one really understands generally. But he did prove it by graphing it. Kind of prove it.
Yeah, okay.
This is 12.
Okay. Ooh, x approaching 2. Okay. Okay, it's just 10. The limit is 10, right?
You are saying this one is 10. The limit of this one is 10. But he's asking the average change of the function. The average rate of the change of the function.
I don't really get how to calculate that though.
The rate of the change, you don't hear that much, right? The rate of the change. We will hear it a lot.
Know what the rate of change is. It's just like
Well, rate of the change is just the change for y from 2 to x, or x minus 2. This is just like a delta y over delta x. Is that it?
yeah.
Whenever you hear rate of the change, it's basically the slope, delta y over delta x.
O Y O O ow. 0 Y O Y. Is that O or is that a triangle?
Delta y over delta x. This is the definition for
Dot?
slope.
You mean delta?
Yeah, delta, yeah.
So you pronounce it like delta.
Oh, yeah. I did pronounce it. So is it making sense? Can I say
yeah.
this is the rate of the
So,
change?
oh, yeah, okay. I get it. And then the rate of change is x minus 2 because it's from 2 to x. So then the rate of change of y is from I still don't really get the rate of change from y, to be honest.
So if I say the rate of change about y from x is dot y over dot x, is that making sense?
It's dot data. Oh, yeah. Yeah, I know, but
how do you pronounce
how do we
it?
find data y? Delta y.
Delta y. Okay. So the delta y is well, I don't really know. So I have to find delta what x minus delta 2. Because this is basically my y1. This is basically my y2. This is basically my y1.
Oh,
Oh,
okay.
yeah.
X minus delta 2. Yeah, but what about,
Delta x is x minus 2.
here?
This is delta y. Here delta y means y2 minus y1, right? And means
Oh, okay.
fx minus f2. So that's why they said from 2 to x.
So then that would mean then F2 is 10.
Yeah.
So I guess it would just be Fx minus 10.
Yeah. Yes.
Okay, do we have any more homework? We have
Oh,
do we have
wait,
any more homework?
we have finished this a little because fx is still here, right? But there is a expression in here, so I can substitute this with x squared plus 3x minus 10 over x minus 2, right?
Okay.
So how to find the limit for this one? Because they say x approaches 2. So I can still use factorization to see whether I can simplify this or not. X minus x plus 5 times x minus 2. So I'm going to simplify
Oh,
this.
yeah.
This is
Okay.
x
Oh,
plus 2
okay, yeah.
plus 5.
Yeah, sorry, I forgot what Fx actually equaled. I was like, okay, it's just Fx, I guess.
Yeah.
All right, yeah, understood.
And then x approximate 2. So this one is approximate 7.
And more about the homework?
Okay. So eventually the rate of the change, every rate of change is 7, okay? For this one. And homework
Okay.
is 877. Let's get the reading property. The last question we did is the rate of the change. Let me see whether they have a rate of the change problem. Oh no, they don't have it. Let's see that it makes sense. Oh, they do have it. Let's do 43.
Okay, so page what, 43?
877. 43. 52.
43, 52.
Yeah. And then 40.
40.
And 29.
29.
And 15. Yeah, that's
15.
all.
Okay. Yeah, thank you.
Am I making sense for the last rate of the change problem?
Yeah, I think it's making sense. It just took me
Okay.
some time to understand.
Sure. We will get this eventually because this is the reason why I learned this, rate of the change, which is the speed.
Yeah, okay.
Okay. That's it then. Have a good day. I hope you have more rest. God bless you.
All right, yeah, bye. Thank
Bye.
you.